share my screen and then we'll get started. Okay, awesome. Could you just confirm you can see my screen?
Confirmed.
Okay, great. With that, I will go ahead and go into present mode and get started. Awesome. Hello, everyone. Welcome to my talk, Taking the Magic Out of ML. Just wanted to thank all of the organizers of TomTom Summit for having me and for organizing this virtual event. So I'm going to be talking about some techniques that you can use to analyze and improve your models. My name is Sarah Robinson. I'm a developer advocate on the Google Cloud team focused on machine learning. If you don't know what a developer advocate does, our job is to educate and inspire, teach the external community about all the different machine learning tools that we have to offer. So that's through a combination of giving talks, building demos, publishing sample code on GitHub, doing blog posts, videos. We also like to take feedback from the external developer community, folks like all of you, and bring that back to our product teams to help improve the product. You can find me on Twitter at srobtweets. I'm pretty responsive on there. You can send me a message. If you've got product feedback, let me know, and I can relay that back to our teams. I also blog about mostly machine learning related things on my personal blog at sarahrobinson.dev. So with that, I want to get started. So the techniques that I'm going to be discussing that relate to analyzing and improving your models all fall under the category of responsible AI. And so I wanted to start out by defining what I mean when I'm talking about responsible AI. So essentially what responsible AI is ensuring that AI machine learning benefits society and doesn't reinforce unfair bias. I'm going to be using the terms AI and ML interchangeably for the purposes of this presentation. So responsible AI is an umbrella term, and within it, there are 4 different fields: fairness, explainability, privacy, and security. And today I'm going to be focused specifically on fairness and explainability. So just wanted to highlight that those are only 2 parts of the larger field of responsible AI, but they're pretty big subjects, and so take a lot of time to cover. So let's start out by defining what I mean when I talk about explainability and fairness. And also these terms are often used together, so I want to make sure that folks understand the distinction between them. So when I talk about explainability, I'm referring to the process of understanding how and why a model is making predictions. So really, going beyond just taking the model prediction at face value and understanding what aspects of this particular example led the model to predict what it did. When I talk about fairness in regards to machine learning, I'm talking about understanding the reasons behind a model's prediction and making sure that models treat all groups of users fairly. So fairness refers specifically to making sure that models are behaving in an equitable way. Explainability is one technique that you can use to uncover fairness issues with a data set or a model. But explainability can also relate to other aspects of a model outside the context of fairness. So just wanted to provide some context for what these terms mean that I'll be focusing on in the presentation. So I want to start with explainability. And the term explainability can evoke many different concepts. Here I'm referring specifically to model explainability, but explainability can also mean different things to different people. This can also depend on your role in an organization. So explainability could refer to transparency, model governance, lots of different concepts. Here I'm specifically referring to the explainability of machine learning models. And when I talk about explainability, what I want to focus on is all the different types of groups of people that benefit from machine learning models. And I've divided this into 3 different groups of people. So the first is model builders and folks involved in operationalizing and deploying machine learning systems. So this could be, data scientists, ML engineers, likely lots of folks that are watching this right now. And so for these folks, explainability can help them answer the questions, why is my model not performing in the way that I expect? Can I explain some strange behavior that I'm seeing in my model, and how can I improve it? The second group of model stakeholders is what I refer to as end users of ML systems. This could encompass a few different types of people. So end users could be maybe somebody that's using an app, that's a shopping application that's giving them product recommendations. In that case, the end user is the person who's getting the recommendations, and maybe they want to understand, why they're being recommended a certain product or movie or thing like that. End user could also be a practitioner. So maybe a medical practitioner or doctor is using the machine learning model to help them with diagnosis given images of x-rays. In that case, the medical practitioner is the end user. And so for these types of users, they are using explanations to understand, should they trust the model's output? Can the explanation give them more confidence that the model is behaving in the way that that person expects? And then finally, using those explanations to understand how to respond and take action from the prediction. The last group involved in a type of model stakeholders is what I'm referring to as public stakeholders. And this is anybody that's involved in regulatory and compliance issues related to machine learning models. So determining if the model complies with certain standards that are in place for whatever industry the model is being built in. Could be healthcare, finance, anything else. They're also using explanations likely to get a higher level summary of how a model is performing to understand if it complies with certain regulations. I'm not going to read through all the examples on here, but these are just some ways that each type of model stakeholder can take action from explanations. So explanations are only one part of the process. The next step is using that data to inform either improving the model, taking action from predictions, or just having a better understanding and more confidence in that the model is behaving in the way you would expect. So what do explanations look like? I'm going to be focusing on just one type of explanation called feature attributions. I'll talk about that a little bit more later on. But just to caveat that the field of model explainability is relatively new. It's emerging. There's new research that we're seeing pretty frequently. So it's an evolving field. I'm going to be focusing on just one type of explainability, but just wanted you to know that there's a lot of different types of explainability out there. Regardless of the type of explainability you're using, this depends a lot on the data type, the type of data that you've used to train your model. And I'll focus on the three most common here: image models, text, natural language models, and tabular models. So this is one example of what explanations might look like for each of these types of models. So starting with the image model, what model explanations can tell us are they can highlight the pixels in an image that cause the model to predict a certain class in this case. So this is an example of a model that was trained on the ImageNet data set, a really large data set with 1,000 different higher level labels ranging from different animals, plants, food, etc. So in this case, the two images on the right are showing us different methods for explaining why the model predicted that this image corresponds with the label husky in this case. So on the left, we see the original image. On the right, two different ways to highlight the most important pixels that contributed to this model's prediction of the label husky. And I'll talk about that a little bit more when I show some demos later on. But basically, in this type of example, we're just using explanations to verify that the model is picking up on the right shapes in the image. So if instead we saw the attributions just maybe scattered randomly around the image or in the background, that's probably a sign we need to go back and improve our training data. So in the text example, in text models, explanations can tell you the words in text that signal the model's prediction. So in this example, we have a sentiment analysis model. And just as an example, I've got the sentence, "How could you not love cake? I love cake." If that wasn't clear. So here we're using explanations to highlight which words contributed to this high sentiment score of 0.9. In this case, it's telling us that the most important words, and we would usually get a numerical value for the importance of each word, but here I'm just color coding it, that not and love were the most important words in this example. And this is one example of how explainability can also highlight fairness issues. So if instead the model was relying on the subject of the sentence, the word cake, that might be a sign that the model is not performing as it should. Because since we have a sentiment model here, the sentiment that the model output should be the same, whatever we change the subject, the word cake to. So if it said, cookies, brownies instead, the sentiment score should be the same. It's really the emotive words like not and love that the model should be using in a case of sentiment analysis. So this was a pretty benign example, but you could imagine how this might play out with identity terms, words that describe a person, with a more of a human-centered data set. So that's one way explainability works for text models. And then the final type of data I'm highlighting here is tabular data. So this is any type of data that you might find in a spreadsheet, numerical data, categorical data. This is the most common type of data for businesses. So in this case, this example is a model that predicts the duration of a bike trip, trained on some publicly available bike share data. And it uses things like some data points about the bike trip, along with the weather data for that given day, to determine how long the bike trip is. And so here for each feature, distance, start time, temperature, etc., we get what's called an attribution value. This tells us how important this feature was in the model making one particular prediction in this case. Attribution values with the highest absolute value are the most important to our model. So attribution values can be positive or negative. Negative attribution values mean that a particular feature pushed the model's prediction down, and vice versa for positive attribution values. So here we want to look at the absolute value to see which features are most important. And this is showing feature importance or feature attributions for one particular input to a model. But you could send a lot of examples, thousands of examples to a model, get feature attributions, and then average those to see overall which features is your model relying on most. So since I work on Google Cloud, I'm just going to show some tools that we have that help you with model explainability today. So just real quick, what I'm showing here is a pyramid that highlights many of our different machine learning offerings organized by levels of abstraction. So the products towards the bottom are targeted more towards data scientists, machine learning engineers, folks that have a little bit more experience with machine learning. And then as we move towards the top, these are tools targeted towards application developers that may want a way to add machine learning to their applications, but don't have as much ML experience. And I'll show you some live demos of both of these types of tools and how you would get explanations from them in a moment. So I mentioned earlier in the presentation that what I showed, the examples of data types in a few slides back, were just one type of explainability called feature attributions. So feature attributions are one part of the larger context of AI explainability, which is typically divided into two categories. Post hoc explainers, and what post hoc explainers are methods for explaining typically deep neural networks, more complex models, that look at the relationship between a model's features and the predicted value for that model to make explanations. And the other type of explainability is usually what we refer to as explainability for models that are interpretable by design. So what I mean by this is typically simpler models with simpler architectures, like linear regression models, decision trees. With these models, the weights, the learned weights of the model carry some meaning about the relationship between a model's features and its outputs. And we can use these weights, learned weights, and other parameters to get insights from a model. In the case of a deep neural net, in the examples that I showed before, a model's learned weights don't carry any meaning in terms of explainability. So they won't tell us, specifically which features the model is relying on. And that's where we would use post hoc explanation methods. So just a little bit of background on all the different types of explainability that are available. So with that, I'm going to go to a demo showing some explanation methods on Google Cloud. So for the first part of the demo, I'm going to show a tool called AutoML. AutoML lets you train custom machine learning models without having you to worry about writing any of the model code. So all you do is upload your data. Once your data looks good, you press train, it trains the model for you, and with AutoML tables, which is the tabular data version of AutoML, which is what I'm going to show, it also has explainable AI built in. So you can see feature importance both for your model as a whole and then for individual examples. So in this example, I took a credit card fraud detection data set that I found in Kaggle. If you're not familiar with Kaggle, it's a great data science platform. Tons of public data sets that are available for you to play with for free. Also data science competitions on there. So if you're looking for interesting data sets to play around with, want a good place to start, Kaggle is a great place. So I took this data set of credit card transactions to see if I could build a model to predict whether or not a transaction was fraudulent or not. The original data set obscured the column names of all of the features in the model since it was real data. So they were just things like V0, V1, V2. So I made up new feature names, which is why you see kind of silly feature names here. So it's all real data. I just changed the names of the features to make it a little bit more interesting to look at. So this is the UI where you would upload your data. So I already uploaded the data set, and here you choose what the label column in your model is, the thing you're predicting, or target column. And then you just train your model here by clicking that button. I'm not going to do that. Now I'm just going to show a previously trained model. So here we get, in the evaluation tab, we get some data on how our model performed, a confusion matrix, which is really important, especially in this case, because this data set was heavily imbalanced. Usually with things like fraud detection, you're going to have very few examples of fraudulent transactions just because of the nature of anomaly detection. It doesn't occur very frequently. So here what we get, AutoML gives us feature importance for the model as a whole. So it looks at the test set of my data and sees overall which features is my model relying on most after generating predictions on all of the examples in the test set. So here it looks like the most important feature is whether there's a smiley face on the signature. Again, these are made up feature names, but you get the idea. So here we can see ranked feature importance, which features are most important to our model. And what this can show us is there are some features that have very little importance here. So one thing I could try in the next iteration of this model is I might be able to try removing those features and seeing if my model performance is any better, if it needs those, or maybe those are important for certain individual examples and I need to keep them in. So here we can also try out our model on a test example. If we go to online prediction here, and I can check this generate feature importance button, it's just populated my features with random values. And let me sort this. So here, for an individual example, I can see which features were most important to my model. For this particular example, it says there's a 99% chance this is not a fraudulent transaction. So in the interest of time, I'm going to move on to the AI platform demo. So I just showed AutoML, which is a tool targeted towards data analysts, data scientists. It's a way to add machine learning to your app without having to worry about that underlying model code. But if you do want to write the model code yourself and have more control over that, we have a set of products to help you do that. And I'm going to show, one sec, our notebook product. And I'm going to jump to this hosted notebook instance that I have. And within this notebook, I have two image models that I want to highlight. Increase the font size so that you can all see this. And here I'm using our Explainable AI tool has an SDK that makes it possible to generate explanations on models that you just have locally within a notebook instance. So it makes the development workflow a little bit smoother because you can generate explanations on a model that you have not yet deployed, which is really handy. So what I'm doing here is I have an ImageNet, a model that I trained on ImageNet just saved in this notebook, in this ImageNet model directory. And I can connect the SDK to that directory. And then it will generate explanations when I pass it a test image. So I'm passing it this test image of a jellyfish. This is what the original image looks like. And we can see, sure enough, my model predicts jellyfish and does so with 96% confidence. But what we want to look at here is the explanations. So what this is showing us is, this is just a key to show you what these colors mean. In bright yellow, we see the most important regions in this image to our model. So in this case, this is a good sign. It looks like the model understands the general shape of the jellyfish. We want to see the important regions, in this case, the jellyfish, which is the focus, highlighted in brighter colors. And it looks like, the background is the least important, which is a good sign. So if we saw different regions highlighted, we might want to use that data to go back and maybe add more training images, making sure we had a variety of training images for every possible label, things like that. In the interest of time, I'm going to skip the chest x-ray example and move on to fairness. So let me go back to the slides. I'm happy to answer questions after, so I'll hop in. I think there's going to be a Zoom after. Okay, so I already showed this. Moving on to fairness, which is another especially important aspect of responsible AI. And to introduce this, I just want to start with a shoe example. So let's say that you're in charge of collecting all the shoe images. Your company is building a fashion classification model. And so your job is to collect a diverse range of shoe images for use in training the model. So think about what type of shoes come to mind. For this example, let's say that I live somewhere that's warm all year round, which is not true. And most people wear sandals all the time. So that's pretty much all I think of when I think of a shoe. So I go about this task. I get a diverse range of different sandals, all different colors, types of straps, soles, etc. I use those to train my model. I run some evaluation on some test images that weren't part of the training data set, and the accuracy is looking really good. But problems are going to start to arise when people that are not from the same place as me try this model out on their own shoes with things like, high heels or sneakers or dress shoes. The model is not going to work correctly. That was, a very simplified example, obviously, but you can imagine how this type of bias finds its way into models frequently. And when we talk about bias, there's different types of bias that can be present in data. The first thing I want to point out is that bias isn't necessarily always bad. There is bias that's naturally occurring. So in the fraud detection example I showed previously, that is an example of naturally occurring bias, where the data set that I used, less than 1% of the examples were examples of fraudulent transactions. And that's just because more data does not exist of fraudulent transactions. That's naturally occurring bias. There are a lot of ways that we can account for this when we build our model, which I didn't get a chance to cover today. But the type of bias that fairness tools typically try to address is harmful bias. So one type of that is data distribution bias, which that's an example. The shoe example that I just described is an example of distribution bias, where we don't have enough examples of all the different possibilities for a particular characteristic. Data representation bias occurs when you do have a relatively equal split of different categories of whatever you're representing in your data, but each of those categories is not represented in a fair way. So let's take the example of we're building a model to predict the sentiment of restaurant reviews. And we have defined all the different types of restaurants that we want to collect reviews for, and we have a relatively equal amount of reviews from all of them. But let's say, for example, that on average, the seafood reviews, restaurant reviews in our data set are mostly positive, whereas reviews for, let's say, vegetarian restaurants are mostly negative. That's really going to be reflected in the model, and that's going to affect the way that new reviews are classified when the model goes into production. Experimenter bias is bias that comes in when you're outsourcing your data labeling, which is pretty common. So machine learning, large data sets are typically better, and it can be very time consuming to label all that data yourself or within your team. So often the task of labeling the data, whether it's images or text, will be outsourced to another team at a different company. And a lot of times labeling can be subjective. There's obviously certain examples where it's not too subjective, but in cases, for example, especially sentiment analysis, Something that I might think has negative sentiment, you might think has neutral or positive sentiment, just based on your surroundings. And so that's what's called experimenter bias. So just from those types of data bias, the point here is that bias can find its way into your machine learning systems in many different ways. So it can occur, in the data collection phase, which is what that previous slide focused on, in the way that your data is labeled. There's even human bias that comes into play when you're building your machine learning model and choosing the error function that you're going to use, or the function that you're going to use to measure your model's quality. So in the case of fraud detection, for example, if I had chosen accuracy as my only metric, then let's say that 99% of the data contain non-fraudulent transactions. So if my model trains to 99% accuracy, there's a good chance it's just randomly guessing non-fraudulent. In that case, accuracy was not a good metric to choose to evaluate my model. And that can lead to, harmful models being deployed to production or models that just aren't performing correctly. Human bias can come into play once your model is deployed and users start interacting with it. So it's just important to be aware of all the ways that bias can affect your machine learning system throughout the machine learning workflow, and just using this to constantly be evaluating your model for these considerations. I'm going to briefly demo the What If tool, which is an open source tool that's built by a team at Google for evaluating your models from more of a fairness perspective. So this is an example of what the tool looks like. You can load it from within Python notebooks. I'm running very short on time, so I'm just going to show a quick demo of it on a data set of mortgage applications. And here I built a simple model on this data to predict whether a particular application is approved or denied. And the data is not being used in this way. I'm just using it for demo purposes. And these are some test data points that we sent our model. And within the What If tool, we can see what our model predicted for a particular data point. We can also edit these feature values and rerun prediction. So I can try, changing the agency that the loan went through, rerunning prediction, and seeing what my model predicts with that updated feature value. Looks like that's taking a bit. Live demos, you never know. I'm going to move to the performance and fairness tab. So what we can do here is we can also inspect our model accuracy on different slices of our data, which is really important to do. So let's say I'm going to look at whether or not the loan was for a home purchase or not. Possible values for this are just 0 or 1. 1 means it was for a home purchase, 0 means it was not. So here I can see how my model accuracy or the percentage of predicted approved loans varies based on this particular feature. So we can see here that loans that were for home purchase had a much higher chance of being approved by our model. And based on whether or not that was intended, we can use the What If tool to take some measures to improve our model. I am short on time, so I'm going to jump back to the slides. That was just a quick preview of the What If tool. Happy to answer more questions about that. One more thing that I'm super excited about that I'll end with is I wrote a book with 2 of my colleagues, and it is being shipped, I think, in the next day or 2. You can pre-order it on Amazon. Just search machine learning design patterns. It covers, so some of the explainability and fairness topics that I touched on are covered in the book, along with many other things related to all parts of the machine learning workflow, from data collection to model deployment. So that's all, some handy links. If there's a way to share slides after, I'm happy to do that. I'll chat with the organizers. And with that, I think I am out of time.